Okay, so now we've got this understanding of what monics look like and how sub-object classifiers work in the category set to the power of C. It's time to start thinking about these kind of logical and set theoretic style operations which are so important in topos theory. So let's start by looking at the idea of the intersection of two monics. So suppose we have a monic little a from capital A to x and little b from capital B to x, say in a general topos for a start. Well, we can think of the intersection of a and b as a subobject of x, and it's really sort of specified by this property here that an arrow h which goes into x is going to be such that, and a intersection b's, we can really think of it as being defined by the property that an arrow h which goes into x is going to be in a intersection b if and only if h is in a and h is in b. So there are, of course, other ways to define the intersection of monics, equivalent ways, but I think this is the most intuitive one. And so now we can basically take this and we can use our inclusion theorem 3 to pretty much directly translate this into something very meaningful for us in the category set to the power of C. So just before I go through the math, let me just show you that the result is really very simple. Basically, for example, in the category of functions, say we have this bouquet X, and then here I'm picturing a subobject A of X and a subobject B of X, and you see the intersection is just a subobject that contains all the vertices and loops which are common to each of these other subobjects. Pretty much the same way as it works in set. Anyway, this idea is formalized for a general kind of category set to the power of C as follows. So we want to compute the intersection of A and B, and why don't we assume that it's an inclusion monic? Because it's only really defined by this kind of property up to equivalence anyway, so we can pick any equivalent ones of the subobjects to represent it. So why don't we think of the case where it's an inclusion monic, in other words, where the set of E-type figures of A intersection B is a subset of the set of E-type figures of X, and then the ETH component of A intersection B, little a intersection B that is just an inclusion function for every object E of C. So we'll look at this kind of case. And in this kind of case, inclusion lemma 3 gives us that the set of E-type figures of capital A intersection capital B, which is the source object of this inclusion monic here, the set of E figures of it is just the set of E-type figures theta of X, which is such that theta under arrow is in A intersection B. And now we can use this result here to know that this is equal to the set of theta in XE, such that theta under arrow is in A and theta under arrow is in B. And then if it also turns out that A and B are also inclusion monics, then we can rewrite this as the set of theta in X of E, such that theta is in A of E and theta is in B of E, which is basically just the intersection of the set of E figures of A and the set of E figures of B. So if we have a look at this picture again, we see it's fairly self-explanatory. The set of loops in the subobject, which is the intersection of A and B, is the set of loops which are simultaneously in A and in B. In that case, that's just this loop down here. And similarly with the vertices of A cap B are the vertices which are simultaneously in A and in B. And here's the same picture, but I've just drawn the actual inclusion arrows. So notice that this is, using these kind of bubbles to represent these different sub-objects is actually usually a lot easier to see. But, really we ought to think of these things as kind of objects outside of the category that are kind of being injected in. And that's really how these sub-objects are being specified. But it's nice to picture them like this, especially when we see how closely the kind of structural intuition we have from working with set theory ties in with this kind of thinking about sub-objects in set to the power of c.